excited to be bringing you a guest speaker, Ted Hallow. I'm going to give you a quick background around Ted, and then I'm going to turn it over to him, and he'll start the presentation. So Ted is a senior defense machine learning engineer at Octo. His current work focuses on the challenges of data concept drift detection, model decay, streaming outlier detection, model explainability, and active learning. There you go. He's perfect for today's topic, I think. So Ted is a former mid-career defense intelligence analyst, a U.S. Army veteran, founder of the Veterans in Data Science and Machine Learning community. He's also the host of the Data Canteen podcast, and he holds a master's in business analytics from the College of William and Mary. Ted has over the past year, I would say, Ted has become a really good friend of our company, and I've gotten to know him on a personal level. He's just a great guy. I love it that we're able to bring a vet on to chat with you guys today. I'm going to turn it over to Ted. Ted, it's great having you presenting today. Welcome. Take it away.
Matt, thank you so much for that introduction. I've been excited about doing this presentation because it's the opportunity for me to give others the introduction to machine learning, drift, and model decay that I wish I had had myself when I first started diving into these topics. So with that, let's get started. Now, this is just sort of our agenda for the workshop. I know I wanted this to be accessible to the broadest swath of people possible. So if you've never touched a machine learning model before, all the way up to if you're a very experienced model builder, you're going to get a lot of good takeaways out of this presentation. So no prerequisite knowledge. Over on the right, you can kind of see the way that we're going to telescope into the topic of model drift and decay. All right, so just to level set and set the context, supervised machine learning, if you're not familiar, it is very simple, really, as a concept. It's an algorithm that learns by example. So quite literally, you give it a lot of example data, and it learns that when it gets inputs like A, then it will give an output like B. And so let's just look at an example here. I've got some sample data that represents airline flights. Each row is an individual flight. Each column is an attribute of the flight. And you can see there's various names that these things go by people in industry. We've got inputs known as predictor variables. And then over on the right, the outputs can also be known as a target label. But the basic idea is that the model learns when I see a flight that looks like this, that has inputs like this, that I'm going to produce an output like that. And over here, these are binary outputs, zeros and ones. This is binary classification. So the task here for this example data was to predict whether a flight would be on time or late. And 0 represents an on-time flight, 1 represents a late flight. And so we have the model learning that flights that resemble this first flight are probably going to be on time. Flights that resemble this second flight are probably going to be late. So that's a basic primer on supervised machine learning. If you weren't familiar, it gets a little bit more complicated when you're doing it for things like computer vision and natural language processing. But at the most basic level, that's how supervised machine learning works. You provide a number of examples as training data, and then the model learns to predict based off of those examples. So there are some implications with this, though, and they're very important. The first, Andrew Ng is always talking about data-centric AI. I think he couldn't be more right about that. Data is king when you're dealing with supervised machine learning. The big issues are quality and quantity. So when you're doing supervised machine learning, there's two problems that can commonly come up. The first one is not having enough data. So if you don't have enough data, then the model doesn't see the examples that it needs in order to make good predictions. And so by having lack of exposure to that part of the problem, then it can't make good predictions about that part of the problem. The second issue is having bad data. So that's where you have example training observations that are conflicting, and the model learns bad patterns, and then it starts to produce erroneous predictions. Okay, so we're about to get into the visual part of this presentation that was promised. I promised a visual explanation of drift and model decay. And I think it's important that those of you who are attending understand that this isn't just a visual analogy. When you take model training data and reproject it into a three-dimensional Euclidean space, this is very much how what you're going to see in this presentation is very much how it really works. And so that makes it great that you can get this intuitive visual explanation, and it's not just an analogy that we'll break down. It's actually a good mental framework and a way to get good intuition about how both drift and decay work, but just how supervised machine learning in general works. Here we've got Dr. Thomas Lux. I've got a quote here from him. He essentially says, all training data exists as points in Euclidean space. We can create an enclosure, then inside that enclosure, we can interpolate. And that was actually very recent. He said that less than a week ago on the Machine Learning Street Talk podcast. There's going to be a number of sources that I will cite as we go through this presentation. You don't have to worry about jotting them down. A slide towards the end, I have all the sources with QR codes. You'll just be able to throw your phone up to the screen and go to any of the sources that interest you. All of them are free online with the exception of one book produced by MIT Press, and that'll take you to the page at MIT where you can purchase that book. Okay, so starting out, it's critical, fundamental to understand that every machine learning problem has a whole problem space. And we can represent that with this blue sphere here on the slide. Now, there's some issues with that, and that are, we already talked about the problems that tend to plague supervised machine learning, the problems of not enough data and bad data. And so if you try to attack the entire problem space, there's a lot more opportunity for these problems to manifest. So earlier we talked about the example of airline flight data. If you try to create a model that would predict on-time or late flights for all airlines, or the whole problem space rather, then you would be trying to predict for all airlines around the whole world, past, present, and future. It'd be very difficult to create a model that could do that. So the key is to neck down your problem. You need to identify what it is that you really, a well-specified machine problem, what it is that you really want to predict, and identify a regional problem space that's a subset of that whole problem space. So if we were, again, going back to our example of airline flight data, maybe we would say we're only interested in airline flights in the United States from the years of 2019 to present. That would be a much better specified problem for supervised machine learning than just trying to build the model generically for the entire problem space of airline data. All right, so what do we say about supervised machine learning models? They learn by example, right? So what we want is we've identified our regional problem space by this little rectangle here that's dark gray. And we want to establish a training domain inside of that so that the training data fully represents the space of the problem that we intend to model. And you can imagine it's much easier to thoroughly collect that data for this little smaller regional problem space than it would be to collect that kind of high density data collection for the entire whole problem space, which would be the rest of the blue sphere. Okay, so if we're successful, what we're going to get is we're going to get a training domain, which is represented by this checkerboard pattern. And it's going to have a good distribution of training examples that cover the entire regional problem space that we want to model. The unfortunate thing is that instead of that, what we normally get is this. When we first do data collection, we get a training domain that covers a good portion of the problem space that we intend to model, but there are a lot of gaps and little alcoves and portions of the problem that we wanted to model that don't actually get represented by the data that we have. And the implications to this are substantial. So it's critical to understand that supervised machine learning models, to include neural networks, in fact, especially neural networks, because that's a nonlinear modeling approach, which is great for real world problems because most real world problems tend to be nonlinear. But nonlinear modeling approaches are always interpolation machines, meaning that within their training domain, they can produce good predictions generally. However, outside their training domain, so out in the part of the problem space that's still dark gray, that doesn't have training domain coverage, they do not do well. They produce very unreliable predictions. And we will look. Oh, it's also worth noting, oftentimes when you're being trained to build machine learning models, anybody who's ever been through formal or informal training, a lot of times you'll get instructions to take your data and randomly shuffle it before you split it into training, validation, and holdout sets. And a lot of people just learn to do that sort of mechanically as just like a recipe that they're supposed to do. But there's actually a good reason for it. And the reason why is if you don't shuffle your data, then your training examples that you end up training your model on are only going to cover, or will likely only cover, a portion of the training domain. Instead of being well distributed, the random shuffling ensures that those training examples cover the entire problem space. So I'm going to take just 1 second before we go to the next slide. I think I see, Matt, do we have some questions?
Yeah, Ted, couple of questions came through. I'll read them to you very quickly. Kamal was asking, in case of very small data sets, for example, less than 1,000, what's the best approach to a predictive model that may actually work? And is even such a model worthwhile? That's the first question.
Yeah, so that's a great question. And what I would say is if you have only a very small data set, that's a perfect application for using a large pre-trained model. And I'm glad that that came up, because that's actually kind of the inverse of what I'm presenting here. What I'm presenting here is if you're building your own models from scratch. If you're trying to take advantage of a large pre-trained model, what that is you have an organization with tremendous compute and data resources, and they have attempted to model the whole problem space. So those large pre-trained models, they are the best attempt to model or establish a training domain for this whole space. But you can almost imagine it like Swiss cheese. So their training domain covers most of it, but there are little holes and gaps here and there. And that's where you take a small amount of your data and update the pre-trained model with the relatively small number of training examples that you have. And then the model becomes competent at predicting on the type of data that you have. So in that case, if you have such a small number of observations, it would be best to try and use a pre-trained model if that's appropriate for the modeling task. Otherwise, I think it is possible to build your own model with with a data set of that size, but quality of the data and consistency of the data are going to be absolutely key. I would refer you to the content that Andrew Ng produced last year on data-centric AI. He talks about this sort of thing. It's possible to do, but the data curation effort has to be of very high quality in order for it to work.
I don't know if this is kind of similar. It kind of dovetails on this. This is a question by Vindra, who asked, how do you know how much data you should need for a good ML model?
Yeah, that's the $10 billion question, right? It's going to be different with every problem. Some problems are more complex than others. And the truth of the matter is, when you first collect data, and that's kind of what this slide is meant to communicate, you don't know initially. That's why we go for big data. We collect as many observations as we can. And then once we have several million, then we think, okay, like surely most types of examples will be covered just out of like quantity, but that's not a safe it's not a safe assumption. And especially considering this is where drift comes in. We're going to go here in just a minute. Things are always changing. So even if you had an exhaustive data set today, that's not going to be an exhaustive data set for the problem as the problem will exist tomorrow or 3 weeks from now or a month from now. So it really does become, and you're going to see this as we go, a cyclic process of updating the training domain, updating the training data within the training domain to keep the model in sync. But I won't spoil the rest of the presentation any more than that, Matt.
All right, sounds good. All right, so why don't you keep rolling, and then we'll take some of these other questions a little bit later on.
Okay.
Thank you.
Okay, so this is another view to show you why interpolation is such a big deal with supervised machine learning and how the training domain plays into that. So we've got the little graphic that we've been working with over here, our regional problem space. Inside of that, we have the training domain and our training data, and it has its gaps. Now, excuse me, I was able to get a fantastic graphic here from the fundamentals of statistics and kind of tie it to our visual that we've been working with. So our training domain here is represented by the same checkerboard pattern that we have over here. The problem space that we don't have data for is represented by the dark gray. Excuse me. And we can actually see the data observations in here, which is really cool. We can see almost a Gaussian normal type of distribution where the bulk of the points are in the middle, fewer points out to the tails, and then we even have a little gap here where there's not particularly great coverage in this part of the training domain. And then when we come up here, we can see the performance of the neural network, and this really puts into perspective the heart of the problem. For the most part, where we have good data coverage, the output of the model, the output of the neural network is reliable. However, we can see in that one little spot where there was a gap, which I've represented over here by this little gap, just with that little spot where there's not any observations or examples for the model to work with, the predictions kind of start to go awry a little bit. And then we can see that when there's no observations to interpolate between, once it gets out into the part of the problem space that's not represented by the training domain, at that point, the model is, I guess you could say, able to extrapolate a little bit when it's very close here on the edges of the training domain. But very soon after you get out into the problem space away from the training domain, the model's ability to produce reliable predictions just falls off dramatically. And so this is why the training domain and your training data is so critically important, and making sure that that training domain is representative of the problem that you actually intend, as fully representative of the problem you intend to model as possible. Because the data plays a proxy type role. It's almost like it's mirroring the problem for your model. And you could think of it like if you had a mirror and the bottom quarter of the mirror was broken off, then the model wouldn't be able to see that quarter of the problem. Similarly, if you have bad data, because we talked about lack of data, if you have bad data, which would be the equivalent of you have a mirror in the middle that's like a carnival mirror where things are distorted, then if the model is looking at the problem through that, then the problem itself is going to become all distorted, and the model is not going to be able to make good predictions. So data playing that proxy mirror role in the middle, it's critical that it be a full and accurate mirror of the problem for your model. Okay, so we had a training domain that was not a great fit for our actual problem space. It had some gaps. Once we trained the model, as I said a second ago, is a perfect mirror reflection of that. It exhibits the same gaps in coverage of the problem that our training domain suffered from. And when your model is out in production, you're going to realize that this is happening because you're going to have certain inputs that come into your model that are going to be problematic or confusing. So let's talk about what a problematic or confusing observation is. So your model is sitting out in production. It's deployed. New observations are coming in. Your model is generating inferences. And if it's a classification model, like what we were talking about with the airline data and models being classified as that are predicted that they'll be late or on time, there'll be some flights that the model is not well prepared to make predictions about. Maybe you'll get a prediction that says, I think that this flight is going to be late with a confidence of 52%. Well, 52% is not very confident at all. That's essentially like a coin flip. What the model is telling you is it's guessing. It's saying, I think it's going to be late, but I really don't know. I'm completely unsure. Could be late or on time. 52% doesn't tell you anything. So that is a great indicator that particular observation is an observation that the model, it didn't have any flights like that one in its training data. Similarly, if you're building a regression model to predict a continuous numeric value, oftentimes when you get an observation that is problematic or confusing for a regressor, the model is going to produce extreme outliers, just completely illogical values. And that's a great indicator for a regression model that that input was problematic and that the model is not well equipped to make a prediction on that type of input. And the reason why is because when those types of inputs come in, the model is essentially trying to extrapolate. And we saw in the previous slide how poorly models do, these supervised machine learning models do at extrapolating. They cannot do it well at all. So what do we do? What's the way forward? The way that you combat this is an approach called active learning. It's one of the ways that you can go about it. It'll be the one that we're going to cover today. And that means that if you have an input that comes into the model and it produces a very low confidence, if it's a classification model or it's an extreme outlier for a regressor, then you're going to take that observation, flag it, set it aside for human ground truth labeling, make best use of the human's ground truthing time, especially if it's like a computer vision problem. Annotating computer vision data is very labor intensive. So you don't want to have humans labeling more examples of observations that the model is proficient at. You want to prioritize that human ground truthing time on ground truthing observations that the model is not proficient at. And then once you have done that, then you're going to take those newly ground truth observations that had previously been problematic. You're going to add them back into your original training set to augment the original training data, and you're going to retrain your model. Before I go on, Matt, did we have any more questions?
Did. I just needed to find the mute button so I could actually talk. So Olivia was asking, there are some ways of inspecting the data to decide between to retrain or not retrain. Can you mention some examples in which it's better to always retrain a model regardless of the characteristics of the data?
Well, so I will tell you this. In practice, any model refitting strategy is better than no refitting strategy. There are places out there that do really well with just having a temporal model retraining strategy. So they've looked at the nature of their problem. They've got domain experts that say, hey, this problem doesn't typically change very much in, say, a 2-week time frame. And then they just set up their model to retrain every 2 weeks. Or, some problems change more rapidly, especially if you're in like finance or something like that. In those cases, maybe you're retraining the model every single day. It's a little bit of a naive approach. And especially if you've got a model that is really important and then you have an abrupt change in the world, but your model has just retrained like last night, then there's going to be a remediation lag where you're just sitting there waiting on the 1 week turnaround time or whatever. All the while your model is sitting out there making bad inferences. So it really is better if you can monitor for the drift and then use that drift monitoring to trigger the model retraining. So it's all intelligent and intuitive and happens when it needs to. But if it's a relatively, if it's a model that's of relatively trivial impact, it's not going to threaten people's lives, then I don't think a temporal retraining regimen is necessarily a bad idea. It's just it's a little bit simple. There are other ways that you can do it by monitoring drift, but those are more complicated. So there's a trade-off there. Are there any more questions, Matt?
Yeah, another one was from Vindra. How do you deal with time series data that has high variability and periodicity changes over fractions of an hour over the day and night?
Yeah, so that's a great question. You would approach it the same way that you would that I'm going to present throughout the rest of this. The difference is that if your data is, or the nature of your problem rather, is changing dramatically over very short periods of time, then that model is probably just going to have to retrain more frequently. But the process itself is the same, whether you're dealing with something that changes frequently or infrequently.
Got it. All right, let's keep rolling. We'll get to the rest of the questions later.
All right, so we use that process of active learning. And if you didn't see that, we had our original training domain. It has all those gaps and alcoves, and there were portions of the problem space that weren't well covered. Once we applied the active learning approach to prioritize flagging and ground truthing those observations that were confusing to the model, then we were able to effectively fill in those gaps. And you get a training domain that much more fully covers and better reflects the problem that you're actually trying to model. So those areas of the problem that the model was previously blind to, now it won't be. Okay, so we refit the model, and as we have represented here, the model now is a really good fit to the problem that we originally set out to model, and it's going to produce the kinds of predictions that we were hoping for. I'll say, if you're keeping track, this is the second time that we've retrained this hypothetical model. And I'll say again that this is a point where MLOps and pipelines are hugely beneficial, because it's one thing to train a model initially. That's a lot of fun. You collect the data and explore the data and experiment with different architectures and hyperparameters. That's all fun the first time you do it. The second time you do it, it's less fun. And it's iteratively as you go, it's less and less fun. So you really want to automate as much of this as you can with MLOps and data pipelines and machine learning pipelines. Because as you go along, you want to keep the bulk of your focus on solving new problems and building models that automate new decision processes, not having all of your bandwidth taken up just by monitoring and maintaining the problems that you solved in days gone by with previous models. And that's what's going to happen if you don't have MLOps employed in the way that you do in production machine learning. Okay, so let's recap real quick. If you have a correctly identified and well-scoped machine learning problem, that's going to define a good training domain. And if you have a good training domain, then that's going to produce the performant machine learning model that you're hoping for. So that's what we've talked about so far. And that's the key foundation that we're going to build on for the rest of this presentation. All right, so now we have to talk about the elephant in the room, non-stationarity. What happens to your machine learning models when the world changes? So modern machine learning models, deep neural networks, they are exquisite mathematical pattern detectors. You train them on examples, they learn those historical patterns, and then they can make good predictions, as long as what happens in the future continues to reflect what was in that training domain from the past. And a lot of, as this quote here from Machine Learning in Non-Stationary Environments, an awesome book from MIT Press, as it says here, much of modern machine learning is built on that assumption. If you've ever been in a formal machine learning class, you've probably been told, just assume that the training data and the test data in production are going to be identically and independently distributed. Here they say that the data generation mechanism doesn't change. Those mean the same thing. That's just not a valid assumption. In the real world, the data generation mechanism always changes over time, and it violates that assumption. And it's really a shame that we train people that way, because it's just not pragmatic out in the real world. And they say here, the final statement, dealing with non-stationarity is one of modern machine learning's greatest challenges. And I think they're absolutely right. So I think that captures the importance of the topic that we're covering here today. All right, so what does non-stationary do to machine learning models? I'm going to replay that animation one more time in case you didn't catch it. As we go into this slide, we had our well-specified model. It was undergirded by a great training domain that had been filled in with active learning, and we had a model that had represented our problem really well. But then non-stationarity happened. Our problem morphed in weird different directions. In some areas it grew, in some areas it actually got a little bit smaller. For the most obvious examples, you could say that this drift for some problems might be like COVID-19 or the 9/11, September 11th terrorist attacks that happened. Those are certainly examples of drift. There are more subtle and insidious types of drift, which we'll talk about a little bit later in the presentation. But for right now, you could think about them as things like that, things that just fundamentally change the world where the model is operating. It's important to note that the models themselves don't change. So when we talk about model decay, that's a little bit of a misnomer. It's the model is static. The problem essentially is that the world around the model is changing. And then when that happens, the model doesn't know what to do with those new patterns that emerge in the world. So you could say that the problem space drifts out of alignment with the existing training domain and model. That would be a great way to understand the problem of drift. Okay.
Hey, Ted, if you don't mind, I'm going to interrupt with one quick question because there's a relevant one from Hartmut who's asking that very question. He's saying, how can I determine if my data is good or bad? His example is interesting because he says, he says, in your example, if I've included all flight data from the time, when that volcano from Iceland blocked most of the airspace and many flights were canceled, would that be bad data?
Well, so that's a great point. It would probably be relevant data for a short period of time, for the amount of time that volcano was continuing to negatively impact flights, because that's going to represent a pattern that emerges, and then that pattern is going to continue for a certain period of time while flights are interrupted. But actually on this slide, we talk about how over time, there's some data that becomes obsolete. It once represented a valid pattern, but then as time goes on, that pattern loses relevance. And at that point, it just serves to confuse the model. That's actually what happens in these areas here that are marked in black on our original problem space. So after the problem space shifted, all of the data that's in this part of the original training domain and in this part of the original training domain, it needs to be pruned away because it's no longer helpful. It's actually hurtful to the model. That's a great example of where more data is not always better. More data helps, but if it's more of the wrong data, it's not helpful. So the trick here, once our problem space has drifted, is that we need to fill in these gaps and we need to prune away these recessions in our training domain. So the same active learning approach that we talked about earlier, where for classifiers, we identify low confidence predictions near the decision boundary. And for regressors, we look for extreme outliers. That is a great way to again, use that process to flag those observations, prioritize them for human ground truth labeling, and then augment the training set once again and prepare to retrain the model. Similarly, at the same time, I would highly recommend employing a temporal weighting scheme to your data such that newer observations receive higher weight and older observations have a lower weight. And you might even have it to where at a certain point, the weighting goes all the way to 0 so that observations that are older than a certain time frame that makes sense for your problem just age off completely, because you can be, in some domains, you can be completely confident that the data has a firm expiration date.
Hey, Ted, let me jump in and ask a question from one of our grads from one of our earlier cohorts, Max. Hey, Max, welcome. He was kind of questioning, he said, wouldn't it be good data if the model has access to news about the geological events and bad data otherwise?
Can you say that one more time?
Sure. He's saying, wouldn't it be good data if the model has access to the news about geological events and bad data otherwise? I'll let you handle that one because I couldn't answer it.
Yeah. So I think if you were going to do some feature engineering or something like that to add features into the model to let the model know that some data was corresponding to a geological event and other data wasn't, then that could work. But otherwise, if you kept the same input features that you originally had, and you just have some flights that are extremely delayed, and because of like the historical data structure, there's no way to annotate that some of those flights were delayed because of the geological event, then at that point, it's in that case that the data would probably not be very helpful later on after the geologic event has run its course.
Great, thank you.
Okay, so after you've employed that active learning approach and applied a temporal weighting scheme to your training data, you're going to be able to prune those parts of the data that are no longer relevant and fill in those gaps. And once again, you'll be able to achieve a training domain that's well aligned with your new problem space, the morphed problem space. So the problem drifted. You had to take action through active learning and a temporal weighting scheme to adjust your training domain to make it reflect the problem. And once you do that, then you can achieve, again, that training domain, that data, it serves as a mirror. As long as it's accurate, you're going to be able to get a model that is a good reflection of the problem because it's looking at the problem through the data. Okay, so as I mentioned earlier, ideally, this really needs to be a continuous cycle. You should be monitoring for drift. You should be able to find out when drift is appreciable. And when it is, then you need to execute that process of using active learning and a temporal weighting scheme to your training data in order to realign your training domain with the problem space. And I'll reiterate for a third time, definitely you need to be employing MLOps and model pipelines and data pipelines in this process. Otherwise, once you get a certain number of models deployed, that's just going to become your full-time job, trying to manually maintain and monitor those models. Nobody wants to live like that. It's not good for you personally. It's not good for the company that you work for. And if you don't have a handle on MLOps yet, I happen to know an awesome guy named Matt Gore. I suggest that you get in contact with him after this because FourthBrain has a fantastic MLOps program that could teach you all about the pipelines and the MLOps processes that you need in order to put all of these concepts that we've talked about here into action. Okay, so we've talked about everything that you need to know to have a good mental framework and intuition for drift and decay, and also how to go about overcoming those challenges in production machine learning. What I want to do for the remainder of the presentation is to dive a little bit deeper. We're going to talk about the two specific types of drift. We're going to talk about examples of each of those types of drift, and then the four modes that those two types of drift tend to manifest in the real world.
Hey, Ted, let me just do a quick time check. We're about 40 minutes in. We got about 20 minutes left. Let me throw one or two quick questions at you. Ashley's been patiently waiting, and some people in the text have been responding to her. So her question was, and this happened earlier in your discussion, I just didn't get a chance to ask it. She was saying, so there are different drifts here, or are they the same, model drift versus data drift?
So there are two types of drift. We're about to get into that. And the names of them, I'll give you the most common names, are concept drift and data drift, but each of them go by other names, and I will have them annotated on a future slide. What it is these phenomenons were originally observed in different fields independently, and the fields assign differing names. And so it kind of depends on which literature you're looking at. If you're looking at a paper that came out of the field of bioinformatics, then it might go under one name. Whereas if you're looking at a paper that came out of a different field, the same type of drift may go by a different name, but I'll try to disambiguate those as best I can here on the next slide.
Okay, great. And then one last quick question. Alejandro, who's actually a graduate of one of our cohorts, was asking, what's the best tooling for detecting drift in production? TensorFlow data, and then he asked TensorFlow data validation question. So I don't know, those might be two separate questions, and I just botched feeding them to you. So the first part was, what's the best tooling for detecting drift in production?
I would say that it's still very much a plane being built in flight. There's a lot more tooling out there now than there was a year and a half ago. The spectrum that it falls on in terms of bad to good is vast. Some of it fully depends on detecting data drift, and we're going to talk about data drift, and I'll try to remember to hit on some weaknesses of focusing solely on data drift. But then concept drift, which is the more accurate of the two types of drift to monitor, it has some challenges as well. So it really kind of depends on your context. If you have a problem where you have rapid access to ground truth labels, then monitoring concept drift and a tool that monitors concept drift is going to be ideal. But in most real world cases, immediate access to ground truth labels is not realistic. In those cases, you're going to have to look at alternative approaches to monitoring drift, because concept drift requires a traditional performance metric in order to work. We'll talk about that more here in just a second.
Okay, great. All right, I'll turn it back to you. Keep rolling.
Okay. All right. So we have the two different types of drift here formally defined. I'll remind you that from our original slide about supervised machine learning, the predictor variables are what we call inputs here on this slide. And in the formal definitions, inputs are defined by X. And then your target label, which is also the model's output, here in these formal definitions, that's denoted by Y. So that hopefully that gives you that context there. Essentially, concept drift is when there is a change in the relationship between the inputs and the model's output. This is alternatively referred to as real drift, which is a great name because that change in relationship between inputs and outputs is what's required in order for an actual drift to happen, in the sense that if you don't have that change in relationship, then the model's performance is not going to be impacted. Now, data drift, on the other hand, which masquerades under all of these alternate names down here, that is a change in the inputs to the model only. Now, and when I say a change, I mean like a change in the statistical distribution. It's the statistical properties of the features. The reason why that, as I mentioned earlier, this is not as good of a type of drift to monitor is because it's very possible. In fact, it happens frequently that there will be changes in the distribution of a feature, and that feature just happens to not be important or a very low importance to the model's overall predictions. So you can end up with a lot of false positive drifts where you're monitoring the statistical distribution of those input features, and there's a change, so you flag it as drift, but in reality, that drift was never negatively impacting the model at all. And so then you end up wasting compute resources and retraining models for no reason and that sort of thing. Whereas concept drift detection, the first type that I mentioned, with that, you're monitoring the statistical distribution of a performance metric like accuracy or error or RMSE if it's a regressor. And you're looking for a change in the distribution of that. And so that's really kind of like the gold standard. But again, as I mentioned earlier, you have to have access to near immediate ground truth labels. And in many cases, that's just not practical. So, there are pros and cons to each of these types of drift and monitoring them. And you really just kind of have to step back, assess the nature of your problem, and then pick the best type of drift detection to monitor for this type of problem that you have and what you have access to in terms of whether you have access to immediate ground truths or not. Okay, so at a practical level, we just talked about that kind of, abstractly. What does concept drift look like? So as an example, I've given you 5 vehicles here. These were brand new cars in 1997. And so we've got a Toyota 4Runner, a BMW M3 Series, Toyota Camry, Porsche 911, and a Honda Accord. We have several attributes about each of these vehicles. These would be our inputs or our predictors if we were using this for machine learning. And then we have the manufacturer's suggested retail price over on the right. That would be our output or our target label. Again, if this was, if we were actually training a machine learning model with this. Now, this is the data in 1997 at the top. Down in 2022, we have the same vehicle. So just assume these vehicles have been kept pristine, never sold, 0 miles put on them. They were put up on blocks in a warehouse by the manufacturer. So there's been nothing to make the value of the vehicle go down in terms of its use. All of the predictor variables remained exactly the same because they were, in fact, 1997 vehicles, but because the vehicles were never used, we can the manufacturer's suggested retail price can be adjusted upwards just in terms of inflation. And inflation is something I think we're all very keenly aware of right now. And inflation is a perfect example of concept drift. With concept drift, you don't have any changes to your input variables, but you have a change in the relationship of those input variables to your target label. So here, the only thing that changed was the MSRP. The MSRP for all of these vehicles is much higher in 2022 than it was when they were first produced in 1997. So by contrast, let's look at data drift. So with data drift, we originally had our 5 new vehicles in 1997. And then we've down at the bottom, we're looking at the same make and model, but these are actual new 2022 vehicles. So the inputs have changed. Unlike before, many of these vehicles have parking assistance and they have tire pressure monitors and backup cameras. None of that stuff was standard back in 1997. And so we can see that the changes to the input variables are actually driving the increase in the MSRP. And that's what you typically see with data drift when it's not virtual drift. Virtual drift is, imagine if we had, I talked about features of low importance for machine learning. So imagine we had a column here and it was color. Color doesn't have much bearing on the MSRP of a vehicle, but you could have, let's say that Toyota decided that blue was not a good selling color, so they totally did away with blue. If you were monitoring for data drift, that would probably flag as a drift because all of a sudden there's no blue vehicles being produced. And then if you're doing data drift detection to trigger model retraining, then you're going to trigger a model retrain because the distribution of blue vehicles has changed. But in reality, that's not impacting your target that you care about whatsoever. But in this case, we actually do have inputs that would matter, and it's the changes in those inputs, all the extra features that these modern cars have are driving the MSRP up. And in a lot of cases, it's if you were paying attention, it actually drives the price up higher than what inflation can justify. So it actually is the features that are driving the prices up, not just inflation. So you can see here, like the Porsche 911, by inflation, the 1997 Porsche should sell today for $129,000 if it's brand new. But instead, you have to spend $140K to get a Porsche 911. And it's a testament to all the extra things we get in cars now, but it costs more money. And then the next thing is, how do these types of drift occur? So these modes are applicable to both concept drift and data drift. When you're monitoring for drift, these drifts can happen abruptly. And that, I gave the example earlier, or examples of COVID-19 and the September 11th terrorist attacks, because those are, everybody can recognize those. It's easy to visualize how those are drifts, but they're very significant and very abrupt drifts that happen at a single identifiable point in time. Alternatively, there's 3 other ways that drift can occur. It can occur incrementally, where it just happens slowly over time. So you instead of going immediately from one state to another, you slowly go from one state to another. The third way is called gradual, and that's where you kind of, for a certain period of time, you bounce back and forth between 2 states, but you start at one state and you ultimately end at another steady state. And then the final type of drift that you'll encounter is recurring drift, where you just kind of continuously bounce back and forth between 2 states or multiple states. And that's very much like, if you're familiar with seasonality, recurring drift is very much like seasonality. Okay, so as we wrap up, a couple of key points to keep in mind. I think the quote from the book produced by MIT Press is critical to keep in mind, and to try to be an evangelist of this quote at your organizations where you work. Dealing with non-stationarity is one of modern machine learning's greatest challenges. I don't think there's ever been anything about machine learning more true that's ever been said. The next thing is, remember what we learned about supervised machine learning models being interpolation machines. As long as the observations that are coming in production fall within the boundaries of the training domain that you have, your model is going to be okay. But as soon as those observations that are coming in fall outside of your training domain, then your model is going to start trying to extrapolate, and you're going to get very low confidence predictions or extreme outliers if it's a regressor. Your model is basically telling you, hey, here's an output, but I'm guessing, I don't know. And that's because these models don't extrapolate well. And finally, the trick is to have that cyclical process, ideally powered by MLOps, to maintain good alignment between your training domain and the problem space that you're attempting to model, and then refitting the model on a regular basis as needed. As promised, here are some great resources for you to check out if you've been interested in this talk and you want to dive deeper. There's white papers here, books, regular articles. There's down at the bottom, there's the reference podcast with Dr. Thomas Luck from Meta. And all of these are free except for the very first one, the book from MIT Press over on the left. I'll pause here for one more minute in case anybody's got their phone up on the screen. Matt, while we wait, are there any questions I can field?
Yeah, I think we have a little over 5 minutes left. So what I was thinking, Ted, could be kind of cool, puts the pressure on you. We're gonna do the speed dating round where I'm gonna do some rapid fire questions at you. I'm going to go through and you're going to give us quick answers to each, just so we can kind of power through some of the outstanding questions. Let me go back.
Let's do it.
All right, that'll be fun. So maybe no more than 30 seconds per question. And everyone, just this is being recorded. We're going to make it publicly available by Monday, the latest. Hopefully, a little bit sooner, but certainly by Monday. I'll also email out the link to everyone that is registered for the event. Okay, let's do it. So first question, and this is kind of a two-parter. This is from Anurag. Anurag, thank you for the questions. So with the weighted data, if there is saturation with the old data and new data now has higher weight, wouldn't that move bias towards new data?
Well, so applying higher weight to the new data would bias it, but that's exactly what you're wanting to do. Now, that's assuming that you're dealing with a problem where the older data is less relevant or not relevant at all anymore. In most cases, for instance, let's go with the airline data that we were talking about earlier. There were radical changes to TSA and the way the airlines work after the 9/11 terrorist attacks back in 2001. So if you had airline data that went all the way back to, say, the early 90s or late 80s, a lot of that predates all the additional security and stuff that was implemented in 2001, it reflects obsolete patterns for your model that no longer play out in the real world, in the post 9/11 world. So that's a great example, I think, of a case where you would probably want to age that pre-2001 data off entirely by taking it all the way down to a weight of 0. And then, of course, with air travel, is very much driven by seasonal travel patterns, when spring break falls, when summer kicks in, the season drives it significantly. So that's a great example of where you'd want to apply very high weight to recent data, say the last 15 to 30 days worth of data, because that's the most reflective of the flights that are happening today and tomorrow, right?
Cool. All right, let's do this. 30 seconds each. Next question from Ashley. Is there a good rule of thumb for how much drift is good or bad as a percentage, say? So is there a general acceptable percentage, she's asking?
I would say no. I think it's all context dependent. If you have a relatively trivial model, no threat to life or limb, then that can probably have a lot more wiggle room, as opposed to if you're doing machine learning models for first responders, to empower doctors doing surgery, to facilitate warfighters in conflict. Those, of course, are very high stakes games. And in that case, you're going to want models you're going to tolerate a lot less drift and retrain more frequently to ensure optimal performance, right?
Makes sense. All right, next question. Sakshi was asking, can we tackle the drift and model decay with cross-validation training methodology? Oh, you get 30 seconds to do that.
It will certainly help. But at the end of the day, it's only going to help out to the full extent of your training domain. And you're almost always going to at least initially have gaps in that training domain. And when that's the case, even cross validation isn't going to help you because you simply don't have data for certain parts to represent certain parts of the problem space.
Great. Kamal, thank you. Some great questions from Kamal throughout this discussion. Why the need to mediate label data to address concept drift?
Can you say that once more, Matt?
Why the need to mediate, he used the term mediate, label data to address concept drift? I can keep going.
Yeah, no. I think I understand the question. So okay. The deal is you're going to have new things that happen. So like, let's say you have an NLP model in the health space that's powering a chatbot. That model can have an exhaustive training set of all English natural language back into history. The model is performing great in February 2020. COVID-19 hits in March. People are rushing to their computers. They're going to the chatbot. They're typing in COVID-19. COVID-19 is a new pattern that the model has no knowledge of. And so that's why you have to use that active learning process to flag those observations of COVID-19 instances where the model is making bad predictions with low confidence, have them flagged and labeled by humans and feed that back into the training set, augment the training set and retrain. And then the model is back in touch with reality. It now has a concept of what COVID-19 is and it can make relevant predictions.
Great. Another great question from Alejandro, who is one of our grads, so we love him. How does this framework extrapolate outside of supervised learning? Does it translate to RL?
I haven't done much work personally with RL, so I probably couldn't speak well to it. I don't want to make any guesses and lead you astray. I know for unsupervised learning, those are typically clustering tasks, kind of totally different situation. They're not even unsupervised tasks, are not dependent on the data at all. They're not being supervised by a target label. So this really doesn't translate to unsupervised problems, but I would leave the question about reinforcement learning to someone with more experience in reinforcement learning.
No problem. Thank you for that. Let's see. There was CSL was asking, will we be able to get access to these resources? Yeah, this is being recorded. The session is being recorded, everyone, and you will have access to it by Monday, the latest. It'll be up on YouTube, and we'll share out that link. Let's see. I'll take one or two last questions. Vindra was asking about, in the example with the MSRP changes, right, that you had with the cars, what in the ML model changes the MSRP? Where is the other input, ? In other words, inflation, minimum prices that they didn't see.
Yeah, so that's the exact thing about concept drift is there's something not captured in the data, some other factor in the world that changed, impacted the relationship between the inputs and the target. And in this case, it was inflation that caused those prices to go up. But it could be any number of things. There are lots of dynamics out in the world that are not captured in the data that end up causing that shift in relationship between the input and the output. It's that very fact that there is a external dynamic that's not captured in the data that causes the drift. I think you're spot on with your intuition with that question.
Excellent. Well, thank you, Vindra, for the question. Ted, we're up on time. This is awesome. Thank you all so much for joining us. We hope you enjoyed this presentation on ML model drift and decay. Ted, thank you so much for presenting, doing a great job as always. Anyone can learn more about FourthBrain. You can visit us at fourthbrain.ai. We have a cohort starting in about a week for our ML Ops program. We have another one starting in April for our machine learning engineering program. You can always learn more at fourthbrain.ai. Like I said, you can also email us at info@fourthbrain.ai. We want to wish everyone good luck on their journey into machine learning and AI. We hope you stay connected to the community. Ted, any parting words of wisdom for our viewers today?
Other than the quote from that book from MIT Press, no, live by that. Matt, it's been an absolute pleasure. Thank you so much for having me on. to do this workshop. And I just appreciate the opportunity of being able to give others the introduction to drift and model decay that I wish I had gotten initially.
Great, great. Pleasure to have you. And thank you everyone for watching. Take care.